Today we'll be going over how to solve the problem called pairing socks on VJudge. It's originally a Kattis problem. So let's start by reading the problem and understanding what we need to do. Simone's mother often complains about how Simone never helps with chores at home. In return, Simone often points out that many of the chores her mother assigns are NP complete to perform optimally, like cleaning the house, seating her little brothers around the dinner table in a conflict-free way, splitting the brothers' Halloween loot in a fair manner, and so on. Being a computer scientist, her mother finds this a fair objection. Looking over her list of potential chores, she picks one she thinks should be easy to solve, pairing a number of different kinds of socks. In the beginning, there are two end socks stacked into a pile. To pair the socks, Simone can repeatedly make one of the three moves. She can either move the sock from the top of her original pile to the top of an auxiliary pile, which is originally empty. 2, she can move the sock from the top of the auxiliary pile to the top of the original pile. And 3, she can pair the top socks from each pile together if they are of the same type. Simone only has one auxiliary pile for a total of 2 piles. There may be more than 2 socks of each type. In this case, Simone can pair them up however she wants. Your task is to help Simone to determine the least number of moves she needs to pair the socks, if it is possible at all. So for the input, we are given 2 lines of input. The first line will contain a number n, which will be half of the number of socks which are contained in the original pile. So there are 2n in the original pile. And the second line denotes the socks where each sock is of the number I. So initially sock 1 is at the top of the pile and sock 2n is at the bottom. What we need to output is the minimum number of moves that she can pair the socks in. And if it's impossible to pair the socks, such as if there's a mismatch, and one sock type has an odd number, for example, or it's impossible to do so, then we have to write out impossible. So we have 3 sample inputs, and let's go over them visually and understand why each of them have the output that they do. So again, just to remind us, we have 3 possible allowed moves. We can either move the socks from the top of the original pile, which is full, to the top of the auxiliary pile, which is originally empty. We can move the socks from the top of the auxiliary pile back to the original pile, which actually we will discuss is that's never actually needed. And the third move that we can do is pair the top socks from each pile together. And each of these counts as a move for our total output. So let's go over this visually for the first test case. As given in the input, we have the first sock being 1, the second one being 2, the third one being 2, and the fourth one being 1. That means that the first stock will be at the top of the pile, and then the last one right here will be at the bottom of the pile. So the idea is that we're going to need to iterate through the length of the first stack, and while it makes sense to use both data structures for the original and the auxiliary as a stack, we can actually do this without maintaining a stack approach for the first pile, because we will never need to move socks back, and I will explain why that is the case. So what we want to do is obviously see if the auxiliary pile contains no elements for the first element, we're always going to want to take the move of taking it from the original pile and putting it on the auxiliary. Once we do this, we add 1 move to our counter. And then now for each of the subsequent steps, what we're going to do is the following. We're going to check if the top of each stack matches, and if it does not match, we're going to keep moving socks over. The reason why we never need to move socks back from the auxiliary pile to the original pile is that if there is a mismatch, then moving the sock back to the original pile simply puts us a move back. It puts us to the step that we were at before we moved the sock from the original pile to the back pile. So we check that if they don't match, we simply just keep moving socks over. We'll now take the top of the original pile and move it to the auxiliary. That's going to add another counter to our move. And then on the third step, what we do is, again, we compare the tops of the stacks. If they are equal, then we can actually match them and get rid of them. And that will also count as one of the moves, because that is part of the allowed moves. So now we have paired these 2 socks, and we need to add another counter to our move. We go to the next step, and again, we do the comparison of seeing if the top of the stacks match, which they do. It's now 1, 1. So we can now pair these socks as well. And we have a total of 4 moves. all socks have been paired, and the way we can check that is if we iterate through the entire original pile and the temporary auxiliary pile also is empty. That's the way we will check if we were able to pair it. If, for example, there was another sock remaining in the auxiliary pile, then we'll check that at the end of the problem, and if the auxiliary pile is not empty, then we'll return impossible. So that makes sense. We got a counter of 4 moves, which is the correct output for problem 1. Now let's look at the second example. For the second example, we're only given an original pile of 3 and 7. So again, 3 is going to be at the top of the stack, 7 is going to be at the bottom of the stack. And we do the same exact procedure. We check, the first step will always have to be moving the sock to the auxiliary pile because there's nothing we can do with 2 empty piles in terms of matching. Let's clear our counter from the last step. So now that we've moved the 3 from the top to the auxiliary, we're going to add 1 move. We then check if these 2 are not equal. They are not equal, and we're going to simply move. Following our instructions, we're going to move the top of the original pile to the auxiliary pile. And now that we've exhausted everything, that's going to give us 2 moves. Now that we've exhausted all of the elements from the original pile, we check and see if both stacks are empty. They are not empty because the auxiliary pile has a 7 and 3, and there's really nothing else we can do to pair these socks because there are no 2 socks of the same kind. So moving back again would just put us in the previous step, so that's not needed. So at the end we check, since the auxiliary pile is not empty, we discard the moves counter and we return impossible. And we can see that that is the correct output for the second test case. Now let's look at the last test case that we have, which is going to be 6 socks of the same kind, 5. Again, first step, we're always going to move the top of the original pile to the auxiliary pile. We add 1 counter to our move. On all subsequent steps, we compare the tops of the stacks. Are they equal? Yes, they are. So we pop from both stacks. And we add a counter to our move. Or we add a move to our counter. Again, next step, since our auxiliary pile is empty, we're just going to simply move from the original to the auxiliary. Add a move. And same as last time, we compare the tops. They are equal, so we're going to pair the socks and add a move to our counter. So we have 4 so far. Same thing, we have an empty auxiliary and we move it. That's another move. And then on the next step, we compare. The tops are equal, so we pair. And we add a move. Last step is to check that both stacks are empty, which they are, so we don't need to print impossible, and we return the counter which we have accumulated. So we have 1, 2, 3, 4, 5, 6. And that is the correct output. So now let's move on to implementing our solution with Python. We will do the first test case, which is going to be the 1, 2, 2, 1 stack. And the first thing we want to do is we want to read the n as input. Next step, we're going to want to convert the input of socks into a list. As I said, we don't really need to maintain a stack for the original pile because we will never need to move socks from the auxiliary pile to the original pile. So we can simply do a list. We're going to use the .split operator to split at empty spaces. And first, let's just check if we have the input correct. So we're going to print n, and we are going to print s. Great, so we have the inputs that we want. We have the 2 right here, and then we have the list, which we have taken from input. And then what we're going to want to do is iterate through the S list and create a temporary stack to store the auxiliary pile. So we'll have a regular list for temp, and we'll treat it as a stack by appending to the end and popping from the top. Then we're going to start a loop ranging through the socks in S. We'll start at 0 and go to n minus 1, because this is the top of the stack at the starting point and this is the end of the stack at the starting point. Oops. Sorry, I'm just fixing that up. Okay. And then the check that we're going to want to do is to see if the top of the stacks match. Also, we're going to, sorry, I forgot, we need to maintain a counter to see how many moves we're going to be taking. So we can use that. We can initialize it to 0. And then we're going to be going through the list and seeing the conditions. So first of all, if the auxiliary stack is currently empty, then the only move we can do is move from the list to the auxiliary. So we're going to check if the length of temp is equal to 0, or if the top element of the temporary pile does not match the current sock we are processing. So we're going to do S of I is not equal to the top element of temp, which is -1. We are simply going to be appending the SI sock, which we are currently processing, into the temp stack. So we'll do temp.append SI. Also, I forgot to mention that at each step, we're going to be adding a move no matter what we do. So we can do that at the start of the loop and just add 1. So if this condition holds, we're going to be moving the sock from the original pile to the auxiliary. If this condition doesn't hold, the only other thing we can do in this case is pop both elements from the top of the stack, because if either of these conditions doesn't hold, it means we can make a pair at that current state in time. We're going to be doing temp.pop, and we don't really need to remove anything from SI because we'll simply be moving to the next sock either way. Then after this loop, we can check if temp is empty. If it is empty, we're going to be returning the counter. If it's not empty, we're going to be returning impossible. Let me just check if we need to print in capitals. No, lowercase. So let's see if our code works or if we made any mistakes. For the first input, we get a number of 4. Let's see if that adds up. That is correct. Let's try now on the second input. For the second one, we get an impossible, which is correct. And for this final one, we expect a counter of 6. Great. Okay, let's try submitting online and see if we pass all test cases. So again, the key insight of this problem was to notice that we'll never actually need to move the talks from the top of the auxiliary pile, because that does nothing for us. Since we can only match from the top, then if we put the sock back from the auxiliary pile to the main, it's simply just putting us a move back. And since we need to find the minimum number of moves, that will never help us. Our solution is accepted. And yeah, thank you so much for watching this.